Yeah, so in the second part, we'll talk about voice biometry. That's my topic of research, which I worked on for, I don't know, like 3 years, 4 years, like a long period of time. And it might not be the most popular topic, but it actually becomes popular each day because now generative models are much better than years before. You can hear and see a lot of deepfake images which are generated, or now deepfake videos, especially with celebrities or some politics stuff. Yeah, so there is there are requests from government to do some stuff like this and so on. And also one secret at EPFL, we will have a hackathon in September, which is not by LauzHack, but we will help with it. And it will also be about deepfakes, probably about face deepfakes or something else. I guess they didn't decide what exactly, but audio deepfakes are kind of similar to what we have in face, in video deepfakes, and so on. Yeah, so in voice, we have so-called voice biometric systems that try to understand whether the speech is a speech of the owner of the system or something else. For example, you all have like a mobile phone with Face ID or Touch ID, and you can open your smartphone using your finger. The problem is that if you use my finger instead of yours, the phone should not open, or if you use my face instead of yours. So this is what is in voice called automatic speaker verification system. Sorry, it is called imposter attack, where one human try to mimic the voice of another human, or just use his or her own voice to try to open the system. So for this, we need a so-called automatic speaker verification system, or ASV, which defines whether a speaker is an owner or another real person. It's important that he or she is real. However, apart from imposter attack, we may have some other stuff which are algorithmic or recorded. Example, in face or fingerprint, I can make a silicone version of your finger, put it on your phone, and it should not open your phone because it's not your real finger. Or in face, if I take a photo of your face and put it in front of your iPhone, it should not open. So in voice, we have synthesized speech, which is basically text-to-speech and voice conversion, which we discussed during the previous lesson. So if I generated synthesized speech from text, it should not open. If somebody says something and then just used voice conversion to make it sound like it was my voice instead of someone else's voice, it shouldn't open. And if you combine both, so you use text-to-speech to generate speech and then voice conversion to make this robot speech to sound more like me, it should not also open. And another thing is called recorded speech or replay attack. It's an interesting one, which seems a bit more complicated. When I record myself, or when you record me on your using some microphone, using in your mobile phone, like you're sitting there and you record what I'm talking about, and then you use my recorded voice in front of the system. So the system will listen to my recorded voice, which is a real voice, and it still should not open because it's not me speaking, it's the loudspeaker of mobile phone speaking. You see? Yeah, so even if I record something on the recorded device and play it back, it should not open. And it seems a bit hard, but we'll cover how to solve it too. So to work against synthesized speech or recorded speech, you need another system, which is called countermeasure system, CM. Now, to have a complete authentication system, you will need to combine ASV and CM into one single solution. So you will have a solution which is capable of defining after imposter attacks, so real humans, and to define whether the speech is real or synthesized, for example. To do so, you create a spoofing-aware speaker verification system named SES. If you read voice biometric systems literature, it might be a bit confusing at first because they use a bit strange terminology. So when they say front end or back end, it's not about like maybe making websites for Google and making algorithms for Google. Front end is about input features. So it can be as a raw waveform, as we discussed, or spectrogram, also called substral coefficients. It's like spectrogram, but a bit different. So as far as I remember, after taking spectrogram, you also apply discrete cosine transforms and again logarithms, so some modified version of spectrogram. And also there are self-supervised embeddings. We will maybe cover them today, or I guess Parse will talk about this in NLP. These are just some models that are capable of transforming your original representation to some compressed representation which contains all the useful information you need. Backend here is what is the actual architecture. It can be a deep neural network. In the old days, it was Gaussian mixture model. So some machine learning method, we won't cover it, but it still occurs in some modern solutions too, but like as a classifier over the deep neural network. Before, it used like a whole thing. Yeah, and your model predicts the score probability of audio being spoofed. Metrics-wise, you have such thing called equal error rate. It occurs only in audio in anti-spoofing, but it is based on the metric which is common in general classification tasks. So equal error rate is about calculating so-called false acceptance rate and false rejection rate. False acceptance is when the audio is actually spoofed, but we say that it is real. So we provide access to a spoofer. We accept him, but or her, but we should. False rejection when we reject access to the owner. So the audio is real, but our model predicted that it is spoof. Given the probability threshold, we can calculate false acceptance rates and false rejection rate for different thresholds. Let's see an example here. So you have several elements on the left. Some of them are with class label 1, some of them are with class label -1. And for each of the elements, you predicted some score, like some probability that this is a spoof, like from 0 to 1. Then you order these elements from right to left, depending on, you sort them. So the elements are now ordered, like this is the element with the smallest probability, with a quite larger, a bit larger, and so on. Now you move from right to left and set a threshold. If your score is higher than threshold, you say that your model believes that this is class number 1. If it's lower than the threshold, class number 0. And by going from right to left, you try different thresholds. So you try different classification results. Like, for example, for threshold somewhere in the middle, all these classes and these classes will be positive, and all this will be negative. And we'll see that some of the classes are labeled incorrectly. Depending on how many classes we classified correctly or not, we will calculate so-called true positive, true negative metrics. I don't remember what's the actual name. So there is actual label, like positive or negative, and there is prediction label.
Is it confusion metrics?
Maybe confusion metrics. Yeah, so for each threshold, you calculate these metrics where you have 4 values. The actual label is positive. How many elements we predicted as positive? So this element will mean how many elements inside our data set are actually positive, and we say that they're positive by the usage of our model. Here, the actual label is positive, but the model prediction is negative, and so on. So we'll calculate this classification table and calculate false positive rate and true positive rate. So false positive rate is the number here. So no, it's the number here. So the actual label is negative, but we predicted positive. So false positive rate is the number here divided by the total number of elements. And true positive rate is the number here divided by the number of elements. And you will create such curve for each threshold. A bit complicated, sorry. Did you understand this? Yeah, hope so. Yeah, so this will create some area, some curve, and some area below it. In classification tasks, usually you can use just this area as a metric of how good your classification solution is. So the ideal solution will have AUK equal to 100%, so it will cover the whole square here. Yeah, and equal error rate, which is used in anti-spoofing, is just a point where false positive rate and true positive rate are equal. So, where true positive rate is 1 minus false positive rate here. So 0.8, 0.2, together they have 1. So this is the equal error rate point on the curve here. You see? Good. Good. Yeah. So let's move to the recorded speech. The setup is as following. You have your system ASV here, and imagine you are staying here as a blue point. So you have some distance from the system, and there is a guy here in the red who records you using his microphone in his mobile phone, for example. So there is some distance between you and the attacker. Then this attacker will go back here, stay in this place instead of blue star, and try to falsificate ASV system using the recorded speech that he recorded. So as you see here, there are some things which may result in that may change the recorded speech in a way that we can detect that it's actually recorded. For example, depending on the distance from me to the microphone, the sound will be different. If you go like too closer to the door, the volume of my speech will be much smaller than if you stay here next to me. Yeah, it will be much quieter. Room size also changes the things because it changes the reverberation. So when we record something in a room, we never record the straight sound as it actually exists. Because when you speak or when you play music or any audio, the sound will reflect from the walls, from the floor, from the cell, from everywhere. And these reflections will go back to your microphone. So apart from recording the actual speech, you'll also record all the reflections. So you actually want to record this red line, but apart from red line, you will record all other lines too. Depending on how long was the path of the reflection, they will come in different time and have different energy. So the fastest way will be the direct sound here in red. There are some paths which are quite short. They will be called early reflections, and sometimes they are useful. So if you design some theater or cinema, maybe you want to have these early reflections because they can emphasize your sound a bit, make it more colorful, like add some timbre, something else. So sometimes they might be useful for you. And late reflections are just noise. So late reflections, they're not like white noise, but they doesn't contain the actual information about the content of your speech. They will just add some other oscillations which are harmful usually are harmful. So one note here, what is the difference between echo and reverberation. So when the reflection is path is too long, the difference between when I say the sound and when it will come back to the microphone will be so long that your ear will hear it twice. So I will say hello, and if reflection path is long enough, instead of saying like hello or something like this, you will hear the complete word hello. This happens because our ear can distinguish sounds which are close to forgot about the ear for now. Yeah, so echo is when you hear two distinct hello, and reverberation when the reflections are so close to each other that you can't actually understand that these are two different reflections, and they will smooth your utterance. It will it will sound like hello, something like this. Yeah, and the reason why it depends on the time difference, because the ear, when the sounds are too close to each other, like 10 or 30 milliseconds, I don't remember, it can't distinguish that these are two distinct sounds. It will blend them. They will mask each other. And in echo, because the difference in time is so long, we'll be able to hear two distinct reflections. Yeah, and in audio, reverberation is a simple convolution. You have a thing called impulse response. In signal processing, impulse response usually is defined like an output of your system when you pass direct delta. And in audio, the definition of impulse response is a clap, or the recording of the clap. So you can't produce direct delta in real life. Yes, you remember direct delta is just like one or infinity, depending on the definition, at the point 0 and 0 everywhere else. You can't make this sound in real life. In order to do something else, instead you clap, or you shoot a gun, or you clap a balloon, break a balloon, and this will create a sound which will be huge at some point and 0 everywhere else. So it's a short sound with a high magnitude at the center. And you will use this sound instead of direct delta. You will record how this clap sounds in your room, and you will use this as an impulse response for your room. Then if you want to make my voice sound like I am in a theater, I will go to a theater, clap my hands, record this. Then I will record myself in a reverberant chamber, so a room, anechoic chamber, so the room where is no reflections. It is possible to get a room with no reflections. Then I will apply convolution of my voice with impulse response from the theater, and the result will sound like I'm in a theater. Okay. Yeah. Apart from clap, another approach is to use white noise, and then at some point turn off the loudspeaker. Because you have reflections, when you turn off the loudspeaker, it won't stop like just when you turn off the loudspeaker. Some reflections will still be covered by your microphone, And you use as impulse response the curve of this white noise, how it goes down in time. Yeah, so as we see, when we record something on the microphone, when we want to record someone else's speech, we can't record it as it really should sound like. We'll get some corruption due to distance from the speaker, due to these reflections. And if our deep learning model can understand this and find these artifacts or from reflection, from the distance, it will be able to distinguish that this is not a real speech. Another thing here is the quality of your device. Loudspeaker in real life can't produce the whole frequency range. So usually your loudspeaker has a good quality for example, 20 hertz to 20 kilohertz, but everything outside sounds bad or will be corrupted. So your loudspeaker has its own frequency response. And when you play something using your loudspeaker, the sound will be different at the end. And that's actually why we can't play direct delta if we even create a synthesized audio which looks like direct delta. If you try to play it, because of if you recall signal processing, so direct delta frequency response will be like this, infinity ones. This is why I remember. And loudspeaker frequency response can be something like this. So your actual output will be like this, not like this. So instead of getting, when you actually try to play direct delta, instead of having waveform which will look like this, because of loudspeaker, it will be something corrupted which looks like this. And that's why it's never possible to actually play direct delta. And if you want to capture a real room impulse response, we need to do some clapping or all this stuff. Questions here?
So what's the way you're using
Immense theory.
No, I know that it is theory. I mean, for your example is fucking hands.
So like we know that in mass theory, in order to get impulse response, we need to pass direct delta through our system. So impulse response, its definition is the output of our system when we pass direct delta to it.
Then you should apply to everything, right? If you want to get the response.
So
for example, in this audio thing.
So let me call it like this. So in a context of the room, the impulse response is how reflections will look like if I pass as a sound this direct delta. Imagine I can use perfect direct delta. So I will capture all the reflections. This will be my impulse response. If I don't move things, this impulse response is constant within the room. Because the impulse response can change only if I change the position of objects in a room. So if I move, this will change impulse response because the reflections will be different. The one reflections which are from me will be different. But if everything is constant, the room impulse response is constant, and I can calculate it only once. I need to calculate it only once. The direct one.
Also, but from the picture that you showed us, like this is like here, can we say that every line is a impulse response, and that's why we should make the impulse response for all these lines?
No. Again, so you have your loudspeaker here and your microphone here. Yeah, if you play direct delta, imagine you can play perfect direct delta. Yeah, you will get some reflections. And you will say that your recording is called H of n. Then, instead of playing direct delta, you will play maybe some music. You will have some other reflections, like they will contain different content, and you will get something we should call x of n. And let's say that music is m of n. The idea here that instead of playing x of n, I can say that x of n is equal to m of n convolved with h of n. So all I need to, like if I know the clean sound without reflections and the impulse response, h of n, I can calculate how this clean music, clean audio will sound inside this room. Yeah, and when I speak, it's actually m of n. But when you record my voice, you will record x of n, not m of n. And because these two sounds are different, you can distinguish whether you get this one or this one. Good? Good. Hope people can see it. Yeah, so the quality of loudspeaker can be different, and it can corrupt your audio less or more, depending on the quality. Yeah, and I didn't include a solution here for the recorded speech because the main approach for recorded speech is just use pre-trained ResNet, like 18, 34, maybe fine-tune it a bit, and that's how you solve recorded speech. There are some more fancy solutions, but I wasn't sure that we'll have time for this, so maybe if we'll have time, I will add it later. But the general solution, use ResNet, and that's all. Yeah, so ResNet is still state of the art in many different tasks, or at least a part of the solution. So your solution based on ResNet or ResBlocks, as we saw in the first part, Hi-Fi GAN, for example, had a lot of these ResBlocks inside, and Hi-Fi GAN is a state of the art. Yeah, moving on to synthesized speech. So synthesized speech is an utterance created via text-to-speech, voice conversion, or both. And one interesting theory behind this is that artifacts lay in subbands, not in the full band. So you have the whole frequency range, and when you apply text-to-speech algorithm, voice conversion, it will lay significant artifacts not everywhere, but in some subbands. Maybe only low frequencies will contain information which is enough to distinguish that this is text-to-speech or voice conversion. Or maybe some middle frequencies, or maybe like one subband here, one subband here. Yeah, and why it is important? Because depending on different front ends, we emphasize information at different subbands. So one thing here is about short time Fourier transform, that we can change the window length and hop length. Depending on the window length and hop length, we can either see clearer the changes in the frequencies or clearer the changes in the time range. So we have to choose what we want to see better, differences in time or in frequencies. And example here, I don't remember what was here. So here maybe it's like 512, and here maybe it's 256. I don't remember. But you see that on the right, we can clearly see distinct lines here. And on the right, or on the left, sorry, they are blurred. So on the left, you won't see different frequencies so well. But on the left, we can see better that there are some strong changes in time. Yeah, so depending on which time resolution or frequency resolution we'll have, we could better distinguish the artifacts in different subbands. So maybe here we'll have little width of subbands, and maybe it's better to detect artifacts. And here, because we have two wide subbands, it will decrease the quality of the prediction. Also, apart from STFT, there are some other stuff like Mel spectrogram, as we discussed. And in Mel spectrogram, it will be a logarithmic scale. So it won't be linear spacing in frequencies, but logarithmic. And it will also mean that we might see better what happens in low frequencies rather than in high frequencies. There is another transform called constant Q transform, which is vice versa. It has something to do with geometric progression. And as far as I remember, it will have like better resolution in high frequencies and worse resolution in low frequencies, or vice versa. So depending on your transform, maybe you can distinguish artifacts in different subbands better or worse. That's why usually you don't have a single model, but a fusion, also known as ensemble. So you have model 1 with some front end, model 2 with some another front end, model n with some another front end. You have either scores or embeddings from each of the models, and you fuse them. So this fusion can be like an average of the scores or weighted average of the scores, or maybe just multiplication, summation, or maybe you want to apply some machine learning above, like linear regression over the whole, all of the scores, or linear regression over all embeddings, or maybe some boosting algorithm, decision tree, and so on. Questions here? Yeah, in non-anti-spoofing literature, it is usually called ensemble. So it's common in other tasks when you have one model that has like one predictions, you have another model that has another predictions, and you combine these two models to have a general solution which has good from the first thing and good from another thing, and it may improve the quality, the accuracy of your predictions. Yeah, let's discuss some of the architectures. The first one is called LauzCNN, and it was created for phase anti-spoofing or for phase detection. So that's another example where you take something from computer vision and apply it in audio and create a paper with this. Yeah, so LauzCNN is just a standard convolutional neural network, so with convolution layer, pooling layer, all this kind of stuff. But instead of using ReLU, leaky ReLU, all these activations, you use a new one, which is called max feature map. So let's see an example here. So in ReLU, maybe it's better if I write it here. So in ReLU, you had your feature map, maybe like 2 minus 3, 4 minus 5. And after ReLU, it will result in 2, 0, 4, 0, because it will ignore all negative values. So that's one of activation. ReLU. Yeah, another called max out. If you have like different channels, maybe 1, 1, minus 1, 10. Yeah, so after ReLU, it will be 1, 1, 10, 0. Yeah. So this first channel, second channel. Yeah, after ReLU, it will be like this. And after max out, it will be only one channel with the maximum element-wise element. So here it is 2, here it is 1, yeah, here it is 10, here it is 4. So max out activation will do something like this. And the proposed max feature map activation will do something in between. So it will work like max out, but not for all channels. It will divide them into 2 parts. So imagine you have, like if you had 3 channels here, max out will provide a single channel for the whole 3. In max feature map, you will divide the input channels into 2 parts, like first and second and third and fourth one. And you will apply max out to the first and third and to the second and fourth. So you will result not in one channel, but in the number of input channels divided by 2. See the difference? Good. Yeah, and FM32 is exactly the same thing, but apart from calculating max, we also calculate median. Yeah.
So depending on what we choose.
Yeah. If you want, we can apply FN to 1, which is from divide by 2 to get 1. Yeah, so it's max out, but pairwise. 3.2 is exactly the same, but it works with the 3 channels, and will produce median and max. Yeah, the cool thing about LauzCNN is that it is actually inspired by some neurobiology. So deep neural networks are called neural networks because some guy originally was inspired by how neurons work in our mind. Yeah, so like fully connected networks are based on this idea that neurons are connected to each other and so on. Yeah, and as far as I remember, in neurobiology, there is some property, I don't remember the name, but it says that your neurons should like pass the information from the neighbors and ignore others or something like this.
Yeah.
Are you talking about it?
I guess so. Okay. You can read the LauzCNN paper, but the thing is that there is some neurobiology stuff, and max feature map activation tries to mimic this idea in deep learning. And it's not like the first case of doing so. Like in source separation task, there is a paper which is called CTCNet, which is also inspired on how your brain perceives the sound, how your brain tries to understand whether it is speech, mine, yours, or someone else, how to split one speech into several speakers. So maybe if you want to create a new architecture, try to look at something like neurobiology and convert it to deep learning domain, try to model it somehow.
And study some physics. That's also right.
Of physics, yeah. Yeah, so as front end here, you can use cepstral coefficients as TFT, so any 2D representation. Another model is called RAWNet2. It's one of these models that actually work in raw domain. So because of the problems we discussed in the first part, deep neural network models in audio rarely work not on STFT-like representations, on raw audio, because working with raw audio is expensive. However, in anti-spoofing, state-of-the-art models are actually working with raw audio. That's because instead of creating these fusion models where you have one front end with one resolution, another front end with another resolution, you make your model to learn itself where are the artifacts located, what subbands it should look on. So when your model works with raw audio, it can do stuff automatically, and this can improve the performance. Yes. So artifacts is like a significant difference in how audio should look like, which makes it look like it's not original audio, something else. So for example, like we know that a good example, we know when people speak, there is a sound of breath, like, yeah, or there is a sound of lips, like this kind of stuff. And text-to-speech models are not capable of modeling this kind of sounds. And for example, we know that in real speech, after we say something, like imagine this like word number 1, word number 2, like maybe here there should be breath, which in frequency domain will look, I don't know, like noise, like something else here. But when we look at the similar audio in text-to-speech, there is nothing here. So this means that if our deep learning model will be capable of looking at these artifacts, so this significant difference between real audio and fake audio, it will be able to distinguish them too. Yeah, so this can be one artifact. Another is silence. Like text-to-speech is not capable of modeling silence properly because it's not trained on modeling silence. Like I didn't want to make silence right now, but you heard it, yeah? So if it was a robot instead of me, it will be a good long sequence without any silence to think about the text and so on. Yeah, and for voice conversion, it is capable of modeling silence because it converts real speech into speech which sounds like someone else, but it can change the content of silence. So if you apply voice conversion on silence, it won't be a real silence anymore. The content of silence will also change. Yeah, so alternative 2 works like this. You have your raw audio, then you have a thing which is called sync layer, which is another version of convolutional layer, which we'll cover in a bit. Then you have several rest blocks, as usual. Future map scaling, FMS, we will cover it. Gated recurrent unit, so some RNN, fully connected layer, and your final score. Yeah, so in general, it looks kind of simple. So some convolution, some rest blocks, some fancy stuff, recurrent neural network, a lot of deep neural network models in audio, either have like transformer inside or look something like this, some convolutions, then some recurrent neural network. Yeah, so sync layer, it's a thing in anti-spoofing and also in speech separation, which is based on a cool idea that you probably don't want to actually learn the first convolutional layer. So in 1D convolutional layer, your result is like this. You have your input xn, you have your filter h of n, and your convolution is this sum. In sync layer, instead of having this h of n with L trainable weights, we will have j of n with only 2 trainable weights, f max and f min. And j of n will be defined like this: 2 f max sync minus 2 f min sync. So sync is just sinus x divided by x. And the thing from signal processing, if you remember it, if you want to get a frequency response which looks like a rectangle, so it's a frequency response, its impulse response should look like a sync. It should kind of like this. Yeah, so when we do this j of n, it allows us to model implicitly model this kind of filtering. So in signal processing, each convolution, so h of n, has its own frequency response, which can be random. Like, it depends on the weights, on what are the trainable weights, but frequency response can look like anything, yeah? And when we use this sync layer, we say that frequency response should look like this. It should be a rectangle. This allows us to directly work with subbands. So if we learned here f min and f max, so our model will learn what are the f min, what are the f max, and the first layer will apply this frequency response on our input. So this will result in an audio that contains frequencies only from f min to f max. And maybe if artifacts are located from f min to f max, this will be, we'll directly look at the artifacts on this subband. Okay, and in real life, we have different channels. Again, one of them has one if min, another has another if max, and so on. So we can look at different subbands and try to find where are the artifacts located. Yeah, and in real life, GFN is smoothed with some window. Again, as we discussed in CFT, you need to apply some window function to smooth the corners. Yeah, so if your original audio had such frequency response, after filtering with sync filter with fmin equal 3200 and fmax equal sample rate over 2, it will look like this. Again, it is symmetric because we discussed in the first lecture that for real input, frequency response is frequency domain is symmetric. Yeah, so we see that we zeroed everything. Oh, no, sorry. Fmin is equal to 0, Fmax is equal to this, and we are left only with frequencies from this to this. Yeah. So when we train convolutional neural network, the first layer in convolutional neural network, because it is designed as a convolution, will actually learn to do some filtering like this. As I draw here, there was some strange filter. So if you train a convolutional neural network and actually look at the weights, at the impulse and frequency response, they will look like this on the left. So there are some noisy responses which kind of try to look at some subbands, but there are several peaks, they are noisy. Maybe we capture a lot of unuseful information. And if we use predefined knowledge from sync layer that we actually want to look at subbands, we can train a convolutional layer that will have responses like on the right, which are much cleaner and actually look at the subband which we want to. Yeah, it was also shown that frequency response from sync layer are more meaningful. For example, if we take all channels and sum the frequency responses for convolutional layer and for the sync layer, we will see that there are some peaks which actually correspond to, for example, here, the average of human speech, like for male and female, the average frequency will be located somewhere here. The first formant, the second formant are like, if you take all the vowels and their formants, as I said in the first lesson, that each vowel has its own frequency response with some peaks which can identify what vowel we said. So if we take average of this for English vowels, we'll get something like this and something like this. So we see that by using sync layer and combining its frequency response, we actually learn something which is meaningful. So it actually tries to learn something about the speaker. And if you look at CNN, there are no such distinct peaks here. Yeah, so the advantages are that we have two parameters instead of L parameters. We have some physical interpretation. We understand what we do. And also we use some predefined knowledge. And it is helpful usually for deep neural networks. Like if you know that that's how people do something, or that's what should be helpful for your model, you can incorporate this knowledge into your deep neural network to help it learn things better. So we knew that in order to work with subbands, it's better to use something like sync filter. We incorporated this knowledge into our model and the performance increased. Yeah, and the conversion speed increased, learned features also increased. Good? Good. Yeah, another thing here is feature merge scaling. In another literature, it is called squeeze and excite, as far as I remember. So the idea here is that you want to perturbate your images, your input feature map a bit to improve the discriminative power of your model. So it will show that if you like add some small perturbations to your feature map, it will be able to learn something. The model discriminative power will improve. Also, here we will rescale each feature map using the global temporal context. And sometimes it is useful to not only look at some local stuff, but use some information from the whole input, some global information, and incorporate it into your local representations. So here in audio, we have CNN feature map, which looks like this, time by filter. So filter is a number of channels, time. And we do global average pooling. So we do average across time to get a vector of length number of filters. And then we apply one fully connected layer plus sigmoid to get something from 0, 1 as a scaling factor. And we apply this S1 on the first channel, S2 on the second channel, and so on. So we rescale our feature map. Notice that here, because we did global average pooling, we actually used global temporal context for this filter. So we rescaled this channel using global temporal context, which can improve our model. Apart from doing simple multiplication, like I said, we can add summation, or we can do sum then multiplication, or we can do multiplication then summing. There are different options. I don't remember the actual properties of them, but like there are a bit different kind of perturbation. Yeah, but the main thing is about adding global context.
Sorry. Yeah, so you consider like adding a Gaussian noise layer in between the feature map and the real layer to be a perturbation itself? Like let's say after you got the feature map of the scene and you add a Gaussian layer.
Gaussian layer that adds some noise and
then after use that instead of doing this. Would you consider this to be the perturbation as well? Then we're doing better.
I never heard of someone doing like this, like with noise.
No, but you can put Gaussian noise layer in between them.
Yeah, I understand what you mean. That instead of adding perturbations like this, you suggest adding some noise. Yeah. But I don't think that it will.
But if it works, then why wouldn't that work?
So this works because we actually also like. There are two things here. First one, perturbation. The second one, global context. This is more important. So because we do global average pooling here, we incorporate global temporal context into each feature map.
That you can still produce with the feature map. The average with the you can produce the feature map with the average global pooling. Let's say you take some inception model and you get the feature map with the average global pooling.
Yeah. And
then use the Gaussian layer.
So instead of doing this scaling factor, you use Gaussian.
Yeah, you Gaussian.
Yeah, but here notice that scaling factor also depends on the channels. So Gaussian noise, no, because you use fully connected layer, the scale factor for the channel number 2 will depend on the average pooling from channel number 1, from channel number 3, and so on. Fully connected layer is connected from connects all inputs to all outputs. So here you have temporal context, you have channel-wise context. If you just do average pooling, then add some noise, you will add perturbations, but they're kind of random, and maybe this will add some global context, but it won't be like so smooth, I would say. Like, yeah. So if you want to add both temporal and channel context, you will use this. There won't be any point to add noise. And also, your perturbations are not random, they're predefined by the values of your in your feature map. I think this is helpful, but I don't want to lie here. So I would say like this. So this is theory-wise looks reasonable. Adding noise seems interesting, but I never saw something doing like this. I suggest you and maybe me to go to Squeeze excitation paper that proposes what the methodology calls squeeze and excite, and see why they say there that perturbations are good. I don't actually remember the good explanation. behind them. Yeah, you had another question.
Yeah, what's the learning signal to get the weights, to tune the weights in the filter?
What's the what?
What's the signal that you use to, what's the loss function?
Here?
Yeah.
Uh,
I don't really care about those functions, but what's
here for final score, because we have a classification task.
So it's going through all of those back propagation.
Yeah, it will go back propagate to this feature map scaling here. Yeah. We have some time. Yeah, we have some time. So, graph neural networks. Usually, when people talk about graph neural networks, they don't think about images and audio. But the interesting thing is that we can still apply them in audio, images, or text somewhere. And we will discuss how. But before we do so, let's understand what is the difference between deep learning, as we discussed in the first week, and graph neural networks. So the first thing is that the order of elements in input doesn't matter. So if we have graph like this and says this is 1, this is 2, this is 3, it won't matter if we have this is 2, this is 1, this is a 3 again. Or even if we don't have this hash. So the whole like visualization of a graph will be exactly the same. We just added some strange numbers here, but these numbers are only for us as humans. That doesn't make any changes in graph because graph is defined by the vertex and the edge. There is nothing about the order in its definition. You see? So when we work with deep neural networks on graph, we also should not care about the order of the elements. That's the first thing. Second thing, we should consider that we have edges. So the output of our function for this node should depend only on its neighbor or on neighbors of its neighbors and so on. So if we have node and say that it depends on some another node, there should be a path in graph that connects these two nodes. Depending on how many edges we have in our graph, depending, like imagine this path has like d edges inside. So this is a path of length d. Then we will process this path in our graph neural network only if the depth of our graph neural network is larger than d, larger or equal than d. So if our graph neural network has depth equal 3, we will consider only paths which are of length 3 or smaller. So if d equal 4, we want base output of function on this node according to this node, because they are too far away from each other. Okay, so yes, the depth of the network is the maximum length of path between two vertices that we consider. One thing here, notice that vertex can depend on itself. Yeah, if I go here and then back, and if my GNN is of depth 2, my node will depend on itself too, because there is like a path like this. Okay, or boom, 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 boom. Given a proper length, I can also depend it like this. Let's look at the example. So you have a graph here, and our neural network, all it does, it modifies the embeddings for each vector, so or for each node. Sorry. So so each of the vertices will have some vector representation. We say that This is x1, maybe this is x2, maybe this is x3. Initially, it can be some random stuff. Then, what our graph neural network will try to do, it will try to change x1 to something meaningful. Let's say it x hat 1, x2 to x hat 2, x3 to x hat 3. And these embeddings now are not random, they are trainable, and they can be used for downstream tasks, like for classification. Maybe if we want to classify each node, like imagine you have a, I don't know, like a graph of diseases and drugs, and you want to define like whether, oh, you have a graph of diseases, they're somehow connected, you have like a class of drugs, and you want to say like what drug should be used on this disease, yeah? Bless you. So you will initialize your model with some random embeddings. Your graph neural network will train these embeddings to get something meaningful, and then you apply some classification on this, like one fully connected layer on x1 to actually get like a class label. See? So for now, let's say that graph neural networks do not change the graph itself. So they don't create new nodes, they don't remove nodes. All they do, they just modify this embeddings. So how it will work? Let's look at the yellow node here. And let's say we have one graph neural network layer. We should consider all the paths of length 1. So the yellow node is connected to the red node, to the green node, and to the blue node. We have them here. If we have 2 layers in our graph neural network, for each of the neighbors, we should add their neighbors too. So blue will depend on yellow, green will depend on yellow, red, blue, and pink, and red will depend on yellow and green. Yeah, so your embeddings will start here. They will modify somehow to modify somehow this embeddings, and this embeddings will modify somehow this embedding. So in graph neural networks, you have this concept of message spacing. So what is message? Message converts your embedding to some other representation via some model. For example, via fully connected layer or something else. And this fully connected layer is exactly the same for all the neighbors inside the layer. So this block, and this block are exactly the same. Like if you have fully connected layer, you transform blue node via one fully connected layer, green node via exactly the same fully connected layer, and so on. When I say exactly the same, I mean the same weights, right? Yeah, so the same weights and bias in your fully connected layer. And aggregation is a function which tries to aggregate new embeddings to create your final embedding here. So because it doesn't, a graph neural network shouldn't depend on the order, you use equivalent fully connected layers here, or maybe convolution, something else. And aggregation should be something which is not order dependent. So maybe it's like average. You calculate embeddings in message, and then calculate average of these embeddings in aggregation function, or maybe summation, or maybe something else which is which doesn't depend on the order. Yeah, and in layer 2 you have exactly the same stuff, but you have another aggregation and another message here. But it's exactly the same within the layer. Questions here? Oh, good. Yeah.
So in each message, there's a set of weighted biases that we.
Yeah. In each message is just some function which is has exactly the same weights and biases and applied for all nodes within the layer. So
the message is.
So for all these three, the message function is exactly the same. But this and this, because they're in different layers, they're different. Yeah, so in general layer 1, you have one message, and general layer 2 will have another message. Well, let's look at the next slide. It will be maybe easier. So initially, your embeddings, zero layer, are equal to node features. Node features, maybe they're predefined in your task if you have some fancy graph, or maybe they're initialized randomly. Then your layer number k plus 1, to calculate the output of layer k plus 1, what you should do? Yeah, sorry, I forgot to say that this is an example of a graph convolutional network. So it's like convolution, but graph convolution. So here, for message, what you do, you take the average of your neighbors from previous layer embedding. So here, yeah, so here your message function can be seen as identity, you do nothing, and your aggregation function is taking average. You take average of embeddings from previous layer. Then you can have something like residual connection, where you use not a neighbor vector, not the embedding for your neighbor, but embedding for your considered node V here. And here you also used identity. And now you have aggregated embedding, you have your residual embedding, and you apply some function on it. Here it is multiplying this by WK and this by BK. And then you apply some activation function on linearity on the whole result. Maybe it's a bit complicated. I would rewrite the equation in a bit different way. So let's say that we have sigma sum over neighbors HUK plus BK HBK. So let's write it like this, so it will be cleaner in a message aggregation way. So here for message, we say that message is equal to multiplication by WK. So message of X is equal to WK X. Yeah. And for each node, which is a neighbor of our V, we apply this message and calculate WK multiplied by HU. Okay. Then we calculated all these messages, and now we aggregate them. As aggregation, we have taken average. So that's one output using neighbors. Let's say it, I don't know, like Y. And this can be seen as a residual connection with some another message here. So we transport a bit our representation from previous layer K. That's, let's say this is Z. And now what we have is a nonlinearity of Y plus Z. Okay. Understandable? Good. I guess in code we will see it better if we have time. I hope so. Yeah, so there is graph attention. It's like attention in transformers, but a bit different. So as I told you in keyword spotting seminar, usually we call attention something when we try to do weighted average, where weights are calculated using some softmax-like operation. So here, to calculate these weights, we look at alphas yj, where I is like ij means that there is an edge from node I to node j. So we take the embedding for node I, transform it somehow, embedding for its neighbor j, transform it somehow, concatenate them, and multiply this by some vector to get a scalar. So it will be a scalar here.
Purposes.
Yeah, it's like some measure of like maybe similarity or something closeness between a connection between one node and its neighbor. And we average and we take softmax of this stuff across all neighbors of vertex I. So this will look like a weighted average where weights are defined like this, or for all neighbors of our considered vertex I. And the final output, new updated embedding for Y will be look like this. It will be sigmoid, or sorry, non-linearity of average over different heads. So like in transformer, we can have multi-head attention. So this is like for one head, but we can have different heads as in transformer. And one head will look like this. It will be some linear transform of the embedding of a neighbor node J multiplied by the weights for this head, which are calculated using this softmax. Okay. Yeah, in the model that we will consider, it looks a bit different. So instead of having concatenation here, they will have element-wise multiplication, then multiplication by some matrix. Also, there should be a 10 activation. It's not written in the paper, but in code there is 10 activation. So you calculate this attention. Your message will be weighted average of embeddings, and your output, also with some residual connection, will be multiplication of your message by some matrix, multiplication of a residual connection by some matrix, taking batch norm of this, and fancy activation seal. The question is, what is graph batch norm? It's a not obvious thing, because your graph number 1 can have 3 vertices, your graph number 2 can have 4 vertices. You can combine them in batch, but they're of different lengths. It's hard to understand like what to do with them. Yeah. So actually, how it works, when you have two, like each of the graph can be represented if you don't consider the edges, we just look at the embeddings for each node. We can say this is a matrix n1 by d, where n1 is the number of vertices in the graph number 1, and d is the dimension of embedding for these vertices. And for J2, it will be n2 by d. Some n2 and n1 can be different. What we can do, we can combine these two graphs into a single one just by reordering the vertices. So if this was 1, 2, 3, and this was 1, 2, 3, 4, let's say that this is still 1, 2, 3, but this is 1 plus 3, this is 2 plus 3, this is 4 plus 3, and 3 plus 3. Yeah, so instead of being 1, 2, 3, 4, it will be 4, 5, 6, 7. And now we look at this as a one graph, just large and not connected. So it has different connected clusters, but in general, it's not connected. Okay. And now we have a matrix n1 plus n2 by d, and we can apply standard 1D batch norm on this J. So like we did in images, on audio, everywhere, we can now apply batch norm here. Yeah, there is such thing as graph pooling. So before I said that we just change embeddings, but it's also possible to remove some nodes to like max pooling operation in the convolution networks. There is graph pooling. So how it looks, we have our matrix-like representation of a graph where we have the number of nodes and the dimension of the embedding. We also have here the connectivity matrix, like which defines whether we have an edge or no. And we multiply this graph matrix by some vector P. So we do some apply some fully connected layer, and also do normalization here to get some vector. When we get this vector, we can take top k elements with the highest value. So, and keep only them. So if, for example, the vertex number 1 and vertex number 3 had the largest value after this projection, we will keep only the first row of our original graph and the third row of our original graph. And we will consider only edges which correspond to the second and third vertices. Okay, this will be our final output. We can also scale it according to these values. Yeah, I guess in our network it will be scaled. Maybe you can ignore this. Let's say that you also scale these elements by the values which were defined here after sigmoid. Okay. Good. Good. Yeah. So our final model for today is called ACIST, and it's a strange application of graph neural networks in audio domain where you are not expected to have it. Why you're not expected to have a graph neural network? Because the thing is, the most important thing about graph is that we don't care about the order of elements. Yeah, so we don't care how we order these nodes. But when we have audio, we know that after this time step, we have this time step. Yeah, so we can't say that this is 2 and this is 1. We need to say that this is 1 and this is 2. So in audio, the order matters. Also in images, if we have an image, we have that there is a pixel here, and we know that this is its neighbor, this is its neighbor, this is neighbor, this is neighbor, but this is not a neighbor for this. So the order again somehow matters. Who would tell me how to solve this, like how to create a graph so we still won't care about the order when we actually care about the order? Yeah, so how you would apply graph neural networks for an ordered input?
Directed edges. It's enough.
No.
There are directed graphs as well, right? Instead of unordered.
I mean, like this. Yeah, maybe we can do it like this. But it will be like a tree. No. Maybe it will work actually. Yeah, okay, this may work. Let's say ordered thing works, but a bit simpler, and when we can easily look at the whole content. So for images, I guess ordered, like you mean like this, it will be ordered. How you would order things in image? Yeah.
It's just reconstructing a convolution built it. So and it's not obvious why the graph representation is helping in the way I'm thinking of it, but yeah, exactly. You only care, you're just doing locality.
Yeah, here.
I don't really care about the direction.
Yeah, but will you have like an edge like this, or only an edge like this, or both edges?
Like,
It depends for who I'm processing. So I can just have in with bound ones, and then I move my filters to somewhere. Ah, I see. We don't want to do that.
Your option.
Maybe you can say they're in order.
But this will make your graph neural network order dependent.
I guess you can like initiate the graph with an order.
Mhm.
And then count itself to bonds between other pixels.
Still seems to be order dependent. Like for audio, I agree that this idea with a direction might be good enough, but for images, it seems a bit complicated to define whether we want to like have such ordered edge or such ordered edge.
instead of like, we define batches of the images, and those batches are represented by graphs, then we can learn,
So you want to like look like this,
yeah.
and
so
then
then we-
how you would connect patches? Like
Yeah, then we can first like, we can create batches in an order. Like
Yeah.
from one to next, and those batches each can be learned with a represented by a graph and on not order.
But okay, your patch is just a smaller image. You will still have a problem that you need to somehow represent your smaller image as a graph.
Resolution, we have to choose where the order doesn't matter for the image.
Okay. This could be possible. It's small, so small that
Yeah, so
the order.
The order doesn't matter.
Yeah, okay, this is possible, and
What about using?
so only the neighbors here.
Yes, like as it's you have your, yeah, you have, let's say we're looking at, let's call it letter A.
Mhm.
You know what its neighbors are.
Mhm.
And then now say like as a neighbor that's B, for example, then you get some, these neighbors are maybe the whole.
Yeah, but look, like I had some neighbors here, I had some neighbors here. If I maybe, I don't know, shuffle it a bit, maybe flip it, I guess I can still maybe shuffle it a bit, so the image will be different, but the graph will stay the same. So the question was that in graph neural networks, you need to have input which is order independent.
Oh, I remember you once said that it should be a full completance.
Yeah, you know the answer. You knew the answer. So the simple answer is like, if I have graph like this, which is fully connected one, we don't care about the order by design, because each node is connected to all other nodes, and no matter how I shuffle it, how I change it, the graph will look exactly the same because you already have all edges. Everything is already connected. See? So for image or for waveform, like I will connect this, this, and so on. Then I will connect this to this, and so on. Yeah. So if you have data which requires some order, but you want to use graph neural networks, you can either think of some ideas like ordering them, like using, ordered edges. Maybe it will work, but the simplest thing to do is just to connect everything. And this can still work. And assist in anti-spoofing exactly does this. So you start with a raw audio and you process it with RODNet2, a network which we discussed before, but you remove GRU, fully connected layer, and FMS, so you have only sync layer plus some ResNet blocks. Then the output will look like some channels by frequencies by time. Yeah, C by F by T. The next thing you do is to calculate, take the absolute value of this and calculate the max through time or through frequency. You will get, if you calculate the max through time, you will get something of size C by F, and it will be your spectral graph. And if you calculate every max across F, it will be your time representation of a graph. Yeah, so you T will define the nodes, and C will be a dimension of the size of an embedding for each of the nodes. Yeah, so you will have one graph only with frequency information and one graph only with temporal information. Then in ASYST, you pass one graph through one graph attention network, as we discussed before, and some graph pooling, and temporal graph through another graph attention network and graph pooling. Now you get two graphs, JS and JT, and you combine them into a single spectral temporal graph. And instead of having only temporal and spectral edges, you add spectral temporal edges. So you will have three types of nodes. This one is temporal, this one is temporal. You have a temporal edge. Another, you have spectral, you have a spectral edge, and another time and spectral, it will be time spectral edge. So instead of having single graph with just one type of edges, you have you combine two graphs into one graph where you have three types of edges. This is called heterogeneous graph. So apart from having vector, and edge, you have a relation. So like Peter is a friend with Jeffrey, a relation is Jeffrey. And another type of edge could be like, I don't know, like, it's hard to, like Peter don't like dogs, for example. I like dogs, yeah. But for example, I don't like dogs. And another type of reflection, I can connect me and dogs as an edge, but the relation on the edge won't be a friendship. It will be like don't like. You see? And what we can do, we can process each of the different types independently. Yeah, maybe one moment. Apart from having this graph, we will also have a so-called stack node, which will collect information from spectral graph and temporal information from temporal graph. So the stack node here, it has direct edges from spectral graph to it and direct edges from temporal graph to it, but there are no edges from stack node to anywhere else. Yeah, so it is used only to collect information from spectral and temporal graph. Yeah, and one thing here is that you will have two parallel branches that have the same stack node. Here it's shared, but the branches are independent. So the idea is that your one branch maybe will learn some one features, useful features. Another branch will learn some other features. The architecture inside is exactly the same, but you use separate instances of the same model. So yeah, to work with heterogeneous graph, you apply heterogeneous versions of the initial layers. We'll cover this in the code. I hope we have time. But the idea is that at first you only process temporal edges, then you only process spectral edges, and then you only process spectral temporal edges. And then you can, for example, average or aggregate somehow in another way the results from the three independent types of edges. Yeah. So at first you have a graph where edges are defined only by temporal relation, only by spectral relation, only by spectral temporal relation, and you aggregate them to get a final single output instead of 3 different outputs. Yeah, and here in ASYST, you use heterogeneous version of graph attention layer, which we discussed before, and graph pooling after first application of graph attention layer, and residual connection after the second one. After this, you have two graphs, one from the first branch, one from another branch, and you apply element-wise maximum to get a single graph like this. Then you calculate node-wise maximum and average across blue nodes, temporal nodes, node-wise maximum and average across spectral nodes. You also concatenate this with a stack node. You will have a lone vector, and afterwards you just use a fully connected layer to do classification. Questions here? Good. Yeah, and final slide, in WAF2Vec2, oh, sorry, in ASYST or in anti-spoofing, the current state of the art is to use ASYST but replace RONet2 with a self-supervised embeddings from WAF2Vec2. So as I said, apart from having spectrograms, vectors, and this kind of stuff, you can also have self-supervised models. And self-supervised models are just models that try to learn some useful representation of the original data. So you have your raw waveform, and instead of having raw waveform, you want to have a small embedding which contains all the useful information about waveform, but is much smaller in size. And we will cover this, I guess, in an NLP lecture. But the general idea of self-supervised models is that, or common idea of self-supervised models is that you do some sort of masking. So here, for example, WAF2Vec2 starts with some convolutional neural network that will produce some tokens for each frame. You will quantize these tokens and apply some transformer. This transformer will have all of these tokens as input, but some of them would be masked. And the output should understand what token was masked. Like it will see that this is masked token, but what was the original value of this masked token? So to try to reconstruct somehow. For now, it might sound a bit complicated. I guess Parse will talk about it better. And I guess the whole idea probably came from NLP. So let's maybe keep it until next Monday and discuss self-supervised models then. I just wanted to say that usually there is the problem that you don't have a lot of data. So, but deep neural network models, they can benefit from having a lot of data. So instead of training your model just on your data set, you use self-supervised model, which is trained on a large corpora, like gigabytes, hundreds of gigabytes of data. It already knows how to represent audio in a good format, so you don't need to learn how to represent it yourself. And you can just apply some classification head or some other head above WAF2Vec2 to do some cool stuff. Like you can use WAF2Vec2 to do automatic speech recognition, as we discussed. You can use it in anti-spoofing and many tasks. Okay, questions here? No. Okay, we have 15 minutes, so let's look at some code. So if you want to do a project in voice biometry, I suggest you to look at this seminar at this section and this section, which define how to write sync layer yourself and what is the data set which is commonly used in anti-spoofing literature. But today we don't have time, and maybe it's not interesting for all of you. So let's go to graph neural networks. And There are some more materials here, but in Russian. Maybe you can use Google Translate to translate them. I think it was originally based on some Stanford course, so maybe you can find an open course from Stanford about graph neural networks and take information from there. Yeah, so you can write graph neural networks directly in PyTorch using vanilla Torch. And that's actually how ACIST is written. It's written in vanilla Torch, not using some other libraries. But there are several libraries which can help you to write graph neural networks easier and so on. Yeah, one of them is called PyTorch Geometric. To install it, you will need to run this code. I won't run it. We don't have time. Yeah, and each graph in PyTorch Geometric is defined as embeddings. So this graph, this matrix node by embedding dimension and edge indices. So 0, 1 means that the first edge connects vertex number 0 with vertex number 1, unless you, and so on. And this is ordered. So if you want to have unordered, you need to indicate 0, 1 and 1, 0. Yeah, and Torch geometric data is represented as a data class here from this model, and you pass embeddings here, you pass index of edges, and this will look like this. If you want to visualize your graph, you can use a separate library which is called Network X. And PyTorch Geometric allows you to convert your PyTorch Geometric representation to Network X representation just by calling this function. So you call it, and you can draw your graph using Network X. And here, our graph looks like this. So the graph which we created here, yeah, 0, 1, 0, 2, looks like this. Yeah. Then how to do graph neural networks? You have, again, a class, which is a subclass of torch nn.model, as always. And here, it's written a bit complicated, but let's look at it. So conv model here is just a definition of what type of convolutional graph neural network you want to use. So there is like a graph convolutional network that we discussed in the presentation. There are some other methodologies which are also kind of look like a graph convolution, but are a bit different, like a bit different message or a bit different aggregation. Another one is called graph sage, for example. And this just defines what type of class for each convolution you want to use. Then here you have nn.model list, which is like nn.sequential, but doesn't apply everything like sequentially, it just contains all of your models. And to work with nn.model list, here we will need to iterate over it and work with it like a list. So you see here, self-const is a model list. We take its ith element to operate with this, and then we can apply some other functions. So when you don't want to use, model list can be useful in such a way where you want to have, you actually don't need a sequential because you don't apply them sequentially in a standard way. You just want, like, you have models. No, how to say it properly. So maybe you want to apply your model from your list, but then do something else with it, which you don't want to use to write a special nn.model class for. So instead of having an nn.sequential, you have an nn.model list. You take element from your list, apply it, and then do something else. In hi-fi again, they also do something like this because it allows to write code a bit simpler. Yeah, so you create all these convolutions here, and you have post message spacing. So after you updated all your embeddings from random to final values, you need to do some classification maybe on your nodes. So you apply linear layer to do some classification. You apply some linear layers to move from embedding dimension to output dimension, which can be like 2 if you have a boundary classification task. Yeah, and you get data in a PyTorch geometric sense as input. To get its embeddings, you do data.x. To get edges, you do data.edgeIndex. And to work with convolutions in PyTorch geometric, you need to either pass data or x and edge index directly. So you can either do something like this or like this. Yeah. And you update your edges here and do classification here. That's all. Yeah. So again, message spacing is a theory behind graph neural networks. You have message, so we apply some function to the embedding from the previous layer and get intermediate embedding M, which is called message. We aggregate somehow using function which is not order dependent, like sum, mean, maybe taking random element. So aggregation function over messages for all neighbors of our vertex. And update function, it creates embedding for in our new layer using aggregation from the previous step and maybe residual connection, if you want to, with the embedding of our considered vertex. Yeah, and the update function and residual function can be, for example, fully connected layer, something like this. Yeah, let's create graph sage version of the convolution, which will look like this. Notice that we have message as an identity function, aggregation function is a mean function, and this update is a linear transformation. Okay. So how to code it? We should have V1 and V2, W1, W2. We define them here. And in our forward, we at first need to get embedding from the neighbors. To do so, we call a method called self.propagate. Yeah, I forgot to say that in order to create a graph neural network layer, you need to create a subclass of a message spacing class from PyTorch geometric. So in message spacing class, you have a propagate method, which inside combines two other methods. One is called message and one aggregate. So you don't need to define a propagate method. You need to define message and aggregate, and PyTorch geometric will do everything else for you. So for propagate, you need to pass edge indices and embeddings for your nodes. Notice that here we can pass a pair of embeddings. So maybe we want to have one embeddings if it's a start of an edge, and another embeddings if we work on an end of an edge. Yeah. So if we work with edge from I to J, for node I may have embeddings from one matrix and node J from another matrix. Here we pass X and X, meaning that no matter if it's a start of an edge or end of an edge, you should use embeddings from tensor X. Okay? Yeah, so message, as we discussed, is just an identity function. Note that here we passed X and X, but message takes xj and xy. So it automatically changes the variable name from variable name to variable name underscore I and variable name underscore J, meaning that I is a start of an edge and J is an end of an edge. And aggregate here just does an average using a separate library which is called torch scatter, which allows you to take average given your inputs and the indices where to work on these inputs. We'll see in visualization a bit below. Yeah, so to train all of this, you create, as usual, training pipeline. It doesn't, it's not different from how you do it in a standard torch, exactly the same stuff. And if you train it, you will get something like this. So it detrains, accuracy goes high enough. All good, you can look at it at home. So important note, as I said, yeah, note that in self-propagate you have x equal xx, which is equivalent to x having x. First argument here, edge index defines the edges. The second one is defined like this. So embeddings for the left part of the edge and embeddings for the right parts of the edge, as I said. And if when propagate calls message function, it will automatically create variable name I and variable name J variables for your function. So it will automatically have a separate variable for processing start of the edge and the separate variable to process finish of the edge. And the shape of this stuff is equal to the number of edges multiplied by the size of your embedding. Yeah, index argument in aggregation method defines to which vertex I each element from J is connected. So index saves the second row of edge index about J. So you have edge from I to J, and index in aggregate function says, okay, this J, what was its neighbor? What I of this was its neighbor? Yeah, and torch scatter, which did summation or mean, works like this. So you have your input, you have a right part of your edge index, which contains only elements J, and it will say, okay, that this is connected to index number 0. So these three should be summed together to get one output. This is the only one which is connected to 1. So this is only this results in 1 output and so on. So this allows you to do a clever summation according to the edges. Yeah, and the final note here is that instead of writing this aggregation function yourself, you just put write aggregation equal mean inside the super underscore underscore init underscore underscore. So instead of writing this, yeah, I could delete it and here say it would work. So if I use some classic standard aggregation function, I can do it like this. 5 minutes more, okay? Yeah, sorry for being late. Yeah, so from PyTorch geometrics, that's all. Another library is called Deep Graph Library, which might be easier to work with heterogeneous graphs. Another one is called Deep Snap. We won't cover it, but like there are many libraries to work on graph neural networks. There is no like a standard one, and you should choose the one which you find more intuitive or better for your task. So here the picture doesn't show. So let me take it from here. Yeah, so for heterogeneous graph, apart from having edges and vertices, you will have some relations. So your connection will be defined not by a pair of vertex and vertex, but vertex relation vertex, triple. So how this change graph neural networks? We just do regular graph neural network for each type of relation and then apply relation-wise aggregation. So you have embeddings from a previous layer. And for relation 1, maybe you have only one triple, which is A1 R1A, A R1A. And you apply a standard graph neural network layer on this part. And for relation number, and when you combine A and B, maybe you have two relations, one is R2 and one is R3. So then you independently process relation number 2 here, relation number 3 here, and all you have to do is to combine these results somehow, maybe taking their sum or their average. Yeah, so for each relation, you do standard update function, standard message passing, as we discussed, and then you aggregate relations and update. So you apply some aggregation over relations, maybe apply, again use a residual function, maybe a new one. So you could use one one here and maybe another one here, and some another update function. For example, relation aggregation can be just summation. Yeah. So questions here? No. So in DGL, it is also possible to create graph. You start with defining the edges here, like this. You can define the data either for vertices or for edges. And to do so, you say j.end_data, so nodes data. You assign some name, x or something else, you define it yourself, equal to some torch tensor, where the first dimension corresponds to the number of nodes, and all other dimensions can be anything. So it is possible to assign multidimensional embeddings for each node in DGL. So instead of having a vector, you can have, like, for example, a matrix here. And it's also possible to assign different edges, different embeddings. You just change the name. Here it is X, here it is Y, and you have different embeddings. You can put your model on CUDA to work with GPU to make it faster. Yeah, and PyTorch geometric is more similar to PyTorch. So you just write and apply functions yourself. You create a linear layer or maybe convolution layer, something else, and you say self x is equal to self linear layer x, something like this. Graph DGL is a bit different. So it has a function pipeline. So you define functions how to process and connect nodes. You can either use built-in classic functions, so like mean, average, copying, and so on, multiplication, or you can create user-defined functions. So, for example, let's do the same network as we did in PyTorch geometric. We again create an n.linear. And how we do now? We say we need to do this. I don't remember why, but let's say we do it Google in in documentation. I don't remember now. Sorry. So in order to get your data from your graph, you need to use the keyword. Here you don't set the data. Yeah, you can get the data by. So it works like a standard Python dictionary. You can either assign value and by giving a keyword, or you can take the value by giving a keyword. So here we start by saying that n data h is equal to h, which is passed in our forward method. And then we called update all, which combines message function and aggregation function into one. So we say that our message function here is just copying element which is named H to element which is named M. So instead of saying that J and data M is equal something, we can pass the names here and DGL will do everything for us. And in reduce funct or aggregation funct, we'll say, let's do the average. You need to average keywords, values which correspond to the keyword M, and save the result in #_n. Then after we updated everything, we can get the result by doing this. And we can still apply some linear functions if you want to, or some either PyTorch models on the result. And our model now looks like this, maybe a bit clearer. Maybe this looks a bit cleaner than PyTorch geometric, but maybe it's not obvious how it works, so it depends. Yeah, and in the same manner, you can train everything, and you can work with heterogeneous graphs using DGL. For example, your graph looks like this. You have a dog and dog which are friend, relation is friend, and cat is scared of dog, like another relation, so another type of edges. Each of them, depending on what edge type you have, you may have different embeddings. So maybe for relation friend, your embeddings are two-dimensional, and for scared of, your embeddings are one-dimensional. Depends on what you want. So example like this. And if you want to have a relational network the same as we used in previous example, we can use another thing called nn.moduleDict. So this is an example when, apart from nn.sequential and nn.modulelist, you can use nn.moduleDict. And this is a PyTorch version of a dictionary. So you can get layers or embeddings or something from dictionary. And here we say that I want for this relation name to have nn.linear, which looks like this. So I have I have a list of all relations. I look at the relation number I take its name. So here it will be a string, a name of the relation. And I say that this relation will look like this. It will be some linear transform from this number of features to this number of features. So then in forward, all I have to do is to write this for loop, which will go over all relations that I have. So if you look at C E type, it will have source type. So the name of source, like X, Y, whatever we called it. E type, the name of the relation. Destination type, the name of the final variable, the final node. And using moduleDict, we can use these names to efficiently understand what layer exactly we want to choose. So we say that we want to update JNode's data with this name according to this value, which we got here. And then we define funcs E type. So this is a funcs. It's another dictionary which contains information what to do with each relation. So with relation E type, we should do this thing. Like again, copy and do in average like we did in the previous code. After we defined all funcs for all relations, we call multi-update all based on these funcs, and we say how we want to aggregate all relations. For example, here we want to take summation of all the funcs. Yeah, that's basically all. Questions? I understand that you probably need to go through the seminar yourself and read the code yourself, spend a bit more time on it. Yeah, so if no questions, thank you all for coming.